Imagine a computer power so vast. It can crack encryption codes in the blink of an eye, simulate complex chemical reactions with unbelievable accuracy, and revolutionize fields like medicine, finance, and artificial intelligence. This is the world of quantum computing. A world where the laws of physics and the limits of technology are pushed to their farthest boundaries. Now get ready to discover it, but before we see how it's different from classical computing, we have to dive into the quantum part of it. Quantum computers work on two very important ideas of quantum mechanics: entanglement and superposition. These two things are the underlying principles that allow quantum computers to perform certain types of calculations that classical computers can. So what is it? Let's start with entanglement. It's a phenomenon where two particles can become so closely connected that the state of one particle is dependent on the state of the other. So imagine you have a pair of magic dice. These magic dice are kind of connected. They always know what number falls on the other dice and then show the same number. It doesn't matter how far you take them apart, the numbers on them will always be the same. How is it possible? Who knows? It's magic. It's basically entanglement in quantum physics, only in this case we're not talking about magic bones but particles. We can take one particle to Mars and leave the other on Earth, but somehow one particle will always know what is happening to the other and change depending on it. That means that if you measure one particle, you instantly know the state of the other particle regardless of the distance between them. Einstein famously called it spooky action at a distance. But scientists have been able to demonstrate this effect in real-world experiments. The recent Nobel Prize winners of 2022 prove there is no error in experiments, and we cannot explain this phenomenon by classic physics. Now let's discuss superposition. Superposition is the ability of a quantum system to be in multiple states at the same time until it's measured. So imagine you're playing a game of rock, paper, scissors with a friend in classical physics. The outcome of each round can only be rock, paper, or scissors. But in quantum physics, things can exist in multiple states at the same time. So, in a game of quantum rock, paper, scissors, your hand could be in a superposition of being rock and paper and scissors all at the same time, and it's only when you actually make a move and your friend sees it that the hand chooses its state. Ha, crazy, isn't it? You may remember the famous Schrödinger's cat experiment. The cat in the box was in the state of superposition. It could be alive and not at the same time until the box is open. And we observe the result. Now don't worry, it was a thought experiment. That cat is fine. These two principles of quantum computing allow for a completely new way of computing. It has the potential to revolutionize the way we process and store information. For example, classical computing uses bits, such as ones and zeros, to represent and manipulate data, everything inside the computer. The messages that you write, the programs that you open, and even this video basically represent very long streams of zeros and ones. A bit is always either a 0 or a 1. It's like a light switch that's either on or off. But in quantum computing, we use qubits. There in the state of superposition. In other words, they can exist in multiple states at once. Is as if the light switch could on/off and everything in between at the same time. Now imagine you have this qubit that's in superposition, and then you entangle that qubit with another qubit. And just like with our magic dice, now the state of one qubit is dependent on the state of the other qubit. To put it simply, superposition allows our qubits to exist in multiple states at once, and entanglement allows multiple qubits to work together in all those states. Can you imagine the things that a computer could do that's far beyond our classical computing? It's like having a magic genie who fulfills all your wishes at the same time instantly, and that's why quantum computing is so exciting. These computers also have the so-called quantum algorithms. These are sets of instructions that you give the computer so it can perform some specific tasks. The most important ones are Shor's algorithm, Grover's algorithm, quantum machine learning, and so on. Wow, Grover's got his own algorithm. Let's take the Shor's algorithm. For example, this thing is a game changer when it comes to breaking encryption codes. Imagine you're a spy trying to crack a secret message, but the code is so strong that it would take a classical computer millions of years to crack it. But wait, you've got a secret weapon, a quantum computer. Just use superposition to try out all the possible combinations at the same time. It's like having a magic decoder ring that can unlock the secrets of the universe in no time. As for Grover's algorithm, it's like having a superpowered search engine. Imagine you're trying to find a needle in a haystack, but this haystack is so big that it would take a classical computer forever to search through it. But with Rover's algorithm, a quantum computer is like having a superpowered Google that can find the answer to any question in seconds. It'll find your needle much faster than a regular computer would. We could also use this to create complex simulations. This would really help us make scientific breakthroughs. Titanic quantum computers can process and analyze large amounts of data much faster than any classical computer ever would. We could potentially solve problems that were once thought to be impossible. We could also combine it with our other achievements like artificial intelligence. Quantum algorithms could help AI systems learn much faster. We could have tons of cool things, from self-driving cars to intelligent chatbots. Now the best part is we already have a couple of real quantum computers. They're even capable of doing some work, but of course they're still far from fully operational models. There are some huge challenges in quantum computing we have yet to overcome. One of the main challenges is the number of qubits. The more qubits you have, the more powerful your quantum computer will be. However, the more qubits we have, the more difficult it is to control and stabilize them. This can lead to errors and decrease performance. We can solve this problem by using more advanced error correction techniques. Another issue is the coherence time. The coherence time is basically how long a quantum computer can keep its superpositions without them getting disrupted. The longer it is, the more calculations the computer can do. But right now the coherence time is quite short, and the scientists are trying to find new ways to make it longer. But despite these challenges, we've made a lot of progress in recent years. Companies like Google, IBM, and Rigetti have built quantum processors with tens of qubits. There are even a few processors with over 100 qubits. And recently in Japan, they started selling the first quantum computers for the average user. These are small quantum computers, each with 2 to 3 qubits, but it's still a huge breakthrough, and even though this technology is still new, the potential of quantum computers is vast. Scientists believe that quantum computers will soon be able to solve problems that are currently impossible for classical computers, leading to breakthroughs in all areas of life. It's the future, and we're just scratching the surface of what's awesome, so let's dive deeper and discover the unknown together. That's it for today. So hey, if you pacified your curiosity, then give the video a like and share it with your friends.